Hello and welcome to this final lecture on the modeling of phonics. So in this last lecture, we're going to look at a model for the plasma concentration, Cp of T, in the case where multiple repeated doses are administered. And this is found in chapter 6 of the type notes. So we start here with the basic model in section 6.1. And here we look at a simple case involving IV administration of the drug, and the administration is at set time intervals. The amount of drug in the body at any given time is assumed to follow a simple one compartment model. So exponential decay dAB by dt is minus KAB, where K is, as before, the elimination constant. In the usual way, we introduce the volume of distribution Vd to obtain the plasma concentration Cp, which is AB over Vd. And so Cp follows the same law of exponential decay. dCp by dt is minus Kcp. We assume, just for the purpose of going through the model, that the first dose is administered at time t equals 0. Successive doses are then administered at times t equals tau, 2 tau, and so on. And this is time measured in hours. And so at a later time, t greater than 0, but just before, the second dose, Cp will be Cp of 0 times e to the minus kt. So here, t is between 0 and tau. So the standard exponential decay. And so if the initial dose is d, then Cp at 0 is the salt factor times the bioavailability times d over Vd. And F equals 1 for IV administration. And so just before the second dose, Cp at time t is SFD over Vd times e to the minus k tau. So the idea here is that we have time t, and we're taking the limit as t goes up to tau. So the limit from below. And I'm just going to write this in a more shorthand notation as Cp at time tau minus 0. SFD is equal to, SFD over Vd times e to the minus k tau. And so just after this second dose, just after the second dose, we have the amount of drug in the body plus literally the shot in the arm, the new dose administered. And so the limit as time goes down to tau, so the limit from above of Cp of t is SFD over Vd e to the minus k tau plus the new dose. And I write this more compactly as Cp at time tau plus 0 is SFD over Vd e to the minus k tau plus SFD over Vd again. And just gather up the terms like so. Now we try and repeat this pattern. So this is where the notation gets a bit dodgy, because I've administered a dose at time 0. The first dose is at time 0. So this time here is the time just before the third dose. So that will be Cp at time 2 tau plus 0 e to the minus k tau. Sorry, Cp at time tau e to the minus k tau. So I have the previous amount and I'm hitting it with exponential decay. So I gather up the terms, and this is SFD over Vd e to the minus k tau into 1 plus e to the minus k tau. And so just after the third dose, at time 2 tau, it's the previous amount plus the new dose. And I gather up the terms, SFD over Vd, and I have 1 coming from here, plus e to the minus k tau plus e to the minus 2k tau. And so on. So I guess the pattern for time 3 tau, so this is just before the fourth dose, that will be Cp at time 2 tau and then hit with the exponential decay factor. And I just rewrite this as follows. And then I guess the pattern that at time n tau, the plasma concentration is SFD over VD e to the minus k tau times a sum. And the sum here goes from j equals 0 to n minus 1, e to the minus j k tau. So I see this as a geometric progression, or a GP. So I use the formula for geometric progression to rewrite the sum in this way, with an e to the minus n k tau upstairs. So at time n tau plus 0, so this is just immediately after this time n tau, a new dose is administered. So this is Cp at n tau plus 0, that's Cp at n tau minus 0, plus the new dose, SFD over Vd. So carrying on from the formula just above, it's the previous amount plus the new dose, SFD over Vd. And I here take a common denominator, 1 minus e to the minus k tau, and I gather up the terms upstairs, and I get a cancellation. So this is the dose, the plasma concentration at time n tau plus 0, so just after a dose, and it's SFD over Vd into 1 minus e to the minus n plus 1 k tau over 1 minus e to the minus k tau. Okay, so let's try and get this ambiguity out of the way. The ambiguity about this labeling on time versus the labeling on doses. So have a look at this figure here. I'm plotting T on the horizontal axis and the plasma concentration on the vertical axis. So dose number 1 is delivered at time 0. Dose number 2 is delivered at time tau. Dose number 3 at time 2 tau, and so on. Yeah. So again, dose 1 at time 0, dose 2 at time tau. And so guessing the pattern, dose n would be delivered at time t equals big N minus 1 times tau. So big N is labeling the dose number. And I just identify big N minus 1 with little n. So rearranging then, I identify big N, the dose number, with little n plus 1. And in this way, I can get the max concentration just after. So this writing here is poor. Just after the big nth dose. And kind of see that from the figure. We look at the maximum concentration. So that's the notation here is new. Cp max just after the nth dose is SFD over Vd 1 minus e to the minus nk tau over 1 minus e to the minus k tau. So yeah, here the idea is that I've got big N, which is the dose number. So big N is identified with little n plus 1. So I get rid of the little n now because it's slightly confusing. And then this is Cp max n. And so the concentration just before the n plus 1th dose will be the previous maximum concentration hit with the exponential decay factor. So again, SFD over Vd, 1 minus e to the minus big N k tau over 1 minus e to the minus k tau, and then hit with the exponential factor. Okay, so here I'll go through a little worked example, and the example is talking about multiple intravenous bolus injections. So 250 milligrams is the dose, and administered every 8 hours, tau, the interval. So the salt factor is 1, the volume of distribution is 30 liters, the elimination constant is 0.1 hours to the minus 1, and yeah, tau is 8 hours. So we want to calculate the plasma concentration 3 hours after the second dose, and also the peak and trough plasma concentrations during this second dosing interval. Okay, so the solution here is just after the second dose. we use the formula for CP max, the one that we rather painstakingly derived. So just after the second dose, we have maximum CP. So SFD over VD, 1 minus e to the minus 2 k tau over 1 minus e to the minus k tau. So that's CP max. And so 3 hours later, I get some exponential decay. So it's CP max 2 hit with some exponential decay. So this is the formula for CP max 2, and then the exponential decay, e to the minus kt, and the t is 3 hours. So I fill in for SFD over VD, 250 milligrams over 30 liters, and then 1 minus e to the minus 2, 0.1 times 8, so tau is 8. And then the 8 downstairs again, and the 0.1 for the elimination constant. And then hit with the exponential factor where the t is the 3 hours. And this works out as 8.96 milligrams per liter. So we also want to have a look at the maximum plasma concentration in the second dosing interval, and we've already done that. It's the formula for CP max 2. So we just fill in the numbers and it works out as 12.1 milligrams per liter. And we also want to look at CP min 2, so the minimum plasma concentration during the second dosing interval. And that would be CP max 2 hit with the exponential factor, and now tau is the dosing interval. So this is the 12.1 milligrams per liter hit with the exponential, e to the minus 0.1 times 8 hours. And this is 5.4 milligrams per liter. So I also want to tell you something about the steady state plasma concentration. So the idea here is to look at CP max n and CP min n in the limit as n goes to infinity. So imagine if you took this drug repeatedly, day after day, then a steady state would happen eventually, where there's a balance between the amount of drug that's eliminated from your body and the amount that's coming in through the repeated doses. So when this balance happens, you're in the steady state. So we just take the limit, CPN max, and the formula, reading back, is SFD over VD, 1 minus e to the minus nk tau over 1 minus e to the minus k tau. And I just take the limit as big N goes to infinity, so this exponential goes to 0. And so the CP max n goes to SFD over VD, 1 over 1 minus e to the minus k tau. So no n's, the n's have gone to infinity. And I identify this with the maximum plasma concentration in the steady state. And the minimum will just be the maximum hit with the exponential factor. This will be CP min in the steady state. We can also look at the ratio of the max over the min. So reading off from the previous two formulae, this is just e to the k tau. So CP max in the steady state over CP min in the steady state. So we can then work out the optimum drug dosing interval for the steady state. Tau is 1 over k times the natural log of CP max in the steady state over CP min in the steady state. And in the same way, we can work out the average concentration in the steady state, CP average. I just take the time average of the concentration, and I average over an interval from 0 to tau, and I look at CPT, but this is somehow in the steady state, and the steady state would be CP max times e to the minus kt. So there's still some time dependence, but the min and the max don't change. So you're averaging between the min and the max. And I do the integral, and it's minus 1 over k e to the minus k tau, evaluate at the endpoints, 0 and tau, times CP max in the steady state, which is SFD over VD, 1 minus e to the minus k tau. And so I evaluate this integral, and it gives me a k and a 1 minus e to the minus k tau, so I get a cancellation. So this works out as SF times d over tau over kvd. And I identify d over tau as a dosing rate. So this is milligrams per hour. Kvd is the clearance. So the average concentration in the steady state is S times F times the dosing rate over the clearance. Yep, and I think RA is called the rate of drug administration, more to use the proper terminology. Okay, and we also identify lastly ultimately the accumulation factor. So that would be CP in the steady state over CP after the first dose. And I just need to decide, should I evaluate this at the peak or the trough? So for example, if I evaluate at the peak, CP steady state will be SFD over VD 1 minus e to the minus k tau minus 1. And after the first dose, at time 0, the amount of drug in the body is SFD over VD. So you get cancellations, and so this accumulation factor is R equals 1 over 1 minus e to the minus k tau. So let me tell you something finally. This is an interesting concept. It's the loading dose. So we call G the periodic dose, the maintenance dose. It's okay to give, I'm not a pharmacologist, but let me just tell you, what the textbooks say. Often it's okay to give a first dose that's higher than the maintenance dose, because this brings about the steady state, which is the desired state. It brings about the steady state more quickly. And so this first dose, which is higher than the maintenance dose, is called the loading dose. So the idea here is, well, to have a look at the figure. So what I've done is I've shown what happens if you don't administer a loading dose. It takes a little bit of time to reach the steady state. But if you administer a first dose so that you start up here, you get to the steady state right away. So we can work out what should be the loading dose to bring about this steady state right away. And it's simply that the loading dose should be your CP max in the steady state. And I just, fill in the formulae, the loading dose again, and here's my formula for CP max in the steady state, SFD over VD, 1 minus e to the minus k tau, but this should be DM now, the maintenance dose. And so I get a whole bunch of cancellations. So the loading dose is the maintenance dose over 1 minus e to the minus k tau. And another way to write this is as the accumulation, R. So the loading dose will be the maintenance dose times R. So that is enough from me about the theory of PK, and it will be over to you in the remaining weeks to look at the exercises and the project.